Hello again and welcome back. In this lesson, I want to show you how rasters can act as 3D data. It's going to be a little shorter and a little more unusual than our typical lessons because I can't actually get the software to work right now. So this is kind of a funny moment, but I think I can still make the point and help you take away something from this. And in the process, we'll do a little bit of a history lesson about how ArcGIS processes 3D information. So first, you don't need to know exactly what's going on my screen right here, but as a brief explainer, it's a piece of software called Blender. It's free, it's cross-platform, and it's a 3D modeling and animation suite. And it's open source, and you can get it online on your own as well, but you don't need to install it for this course. However, it can be useful as you get into GIS to have a 3D modeling suite like Blender or like some of the commercial suites installed. Because you can do things like what I'm doing right now, as well as make more advanced graphics and animations if that's a skill you have. Now, the reason I'm using Blender is because I couldn't get ArcGIS or ArcGIS Pro to display this data correctly due to bugs in both pieces of software. We'll introduce it a little more later in this lesson, but ArcGIS has a piece of software called ArkScene, which is kind of analogous to ArcMap and ArcCatalog, but it's for 3D scenes. And I'm not sure what Esri's official stance on ArkScene is, but my impression has been that it has gotten less attention and has developed more bugs over the past few years, and it isn't as great of a 3D environment as it used to be. At the same time, Esri has made 3D a truly first-class citizen in ArcGIS Pro, which you'll see once you get your hands on ArcGIS Pro, once we get our license situation resolved. That said, ArcGIS Pro is still a young piece of software with a lot of bugs of its own, and Esri is working really hard on it, and my experience with it has been very positive when it works, but I wasn't able to get it to really display the data in any way that I could show you very well in a demo. The data displayed, but wasn't very effective. So on the one hand, ArkScene, the current 3D viewing environment, doesn't work, and on the other hand, ArcGIS Pro isn't quite ready yet. So I'm using Blender. And as a result of this, I can't do some of the interactivity that I want to do, which is to imagine a raster that's a 2D surface, like our digital elevation model for Valmeyer that we've used a few times in the past. If you don't really remember, you could see it over here as a little bit of a preview. And again, the dark in a digital elevation model is usually the low point and the white are the high points, and you can see these river channels. And we're actually looking at this a bit upside down right now. So let's see if I can kind of get us into that viewpoint. Not as effectively as I want. So we'll still look at it upside down, or backward at least. So we're kind of coming up from this side, looking down this way. Anyway, what we have with the digital elevation model is a pseudo 3D structure. While our cells are specifying the X and the Y location just by where they are at, our Z location is actually the data. We're not officially storing a true Z value, but inherently, when we have something like a digital elevation model where the values in a raster represent heights, that is a Z value. We can explicitly set Z values on things in feature classes, and we'll do that later in this lesson, but we can implicitly set Z values as heights on rasters, which is what a digital elevation model does. So we have this structure that's effectively 3D, even though it's stored in a two-dimensional structure, such as a raster. So what I want you to take away from this is that rasters aren't just conceptually 3D either. Even though we display them in 2D in ArcMap, they are truly useful in a 3D context in that we can extrude them, as we do with this 3D model, to have heights in 3D modeling software, or in ArcGIS Pro, or in ArkScene when they function correctly. And when we do this, we get full surfaces. We talk about rasters as surfaces, but we get true surfaces that we can run other types of models on. And not all models need a visual 3D model, but some models, being process simulators, not 3D models, but some models like process simulators need this type of structure in order to incorporate height and elevation and slope into their models too. So you might run a hydrologic flow model on something like this. And having this 3D model lets you view it in a way that humans more intuitively understand. Okay, so since the technology is not cooperating that well anyway, I'm going to keep this brief and just say the real takeaway here is rasters are basically three-dimensional structures if we choose to view them that way in a piece of software that's capable of it. But even still, they are capable of three-dimensional type analysis when we conceptually assign a 3D model to them, like a digital elevation model. A land cover raster isn't really three-dimensional in the same way as a digital elevation model because a land cover raster stores categorical information. But if we assign a continuous surface-oriented value like height to a raster, then it's a basically three-dimensional structure for us. And I want you to keep thinking about ways that that's useful as we go through this lesson. Okay, that's it for this lecture. In this lecture, I showed you a 3D model of our Valmeyer digital elevation model, described a bit of what's going on in the 3D sphere with ArcGIS, and talked about how rasters are conceptually three-dimensional. In the next lecture, we'll talk about building some three-dimensional structures of our own. See you there.